Hello everyone, welcome to another video of MATLAB and Simulink racing launch on tire modeling using extended tire features for Vehicle Dynamics Blockset. Consider you have designed a brilliant suspension, tuned your controllers and built a sleek vehicle model. But when you simulate high-speed cornering or hard braking, the results feel off. The car understeers too much, grip seems unrealistic, and the behavior just doesn't match what happens on track. What could be the issue? Most likely oversimplified tire modeling. Tires are nonlinear, load sensitive, and complex, especially under combined slip, camber, and varying pressure. So, in this video, we will introduce you to the extended tire features in Vehicle Dynamics Blockset, using which you can import pre-processed data, visualize data, fit model, and export it to Vehicle Dynamics simulation formats. Note that there are two approaches to using the extended tire features. The first is the programmatic API approach, and the second is a tire manager app. In this video, we will dive into the details of the API approach and give you a quick glimpse of the tire manager app. Here is what we'll cover in this video. We will begin with a quick overview of tire forces, moments, and angles just to make sure we are all speaking same language when it comes to tire dynamics. Then, we will introduce the extended tire features in the Vehicle Dynamics Blockset. We will also look at how to set up the support package. After that, we will walk through the workflow and key functions involved in the extended tire modeling process. For this, we have created two demos. In demo 1, we will guide you step by step through the full process from importing raw tire data to pre-processing, visualizing, fitting the model, and exporting it to Simulink. This will give you a complete understanding of the workflow. Next, in Demo 2, we will leverage the learnings from Demo 1 and we will focus on some other useful functions like importing different formats of data, splitting and downsampling data, and use the exported tire model in a vehicle dynamic simulation. Finally, we will wrap up the video with some of the resources. Before we jump into the workflow and demos, here is a quick reference to the key forces, moments, and angles we'll be using throughout this video. If you are new to tire modeling, this diagram and table will help you follow along more easily. And if you are already familiar, consider this as a quick refresher. The extended tire features for Vehicle Dynamics Blockset provides a set of tools to work with tire data and integrate tire models into vehicle simulations. With these features, you can import and pre-process data, visualize it, create tire models, perform computations, fit tire data, and export tire models to relevant formats such as TIR files. The toolbox includes multiple functions that we'll be using throughout the demos. In order to install the support package, select Add-ons and then Get Add-ons. In the Add-on Explorer, search for the extended tire features for Vehicle Dynamics Blockset. Then install the support package. Now that the support package is installed, let's get started with our first demo, which is based on an example from the documentation. The extended tire features for Vehicle Dynamics Blockset includes examples that use test data from a mid-size passenger car tire. Data files from each test are stored in the TYDEX format. The data from each unique test procedure and condition is contained in a separate file. And the file name indicates the test type, operating conditions, and sweep directions. We will now switch to MATLAB. As we open the MATLAB window, we can see that the folder containing the tire data is in current folder. In the live script, we have already built a string array from the TYDEX file names that contains the tire data. With the tire data present in the string array, we import it into an array of tire data objects using the file names specified in the string array. Data from each file is stored in a separate tire data object. You can use this function to display the properties of a tire data object. Additionally, you can call out a single tire data object individually. So now that we have successfully imported the tire data and stored it as tire data objects, the next step is to start exploring and visualizing this data to better understand the tire behavior. We will use the plot command to visualize the tire data objects. As you can see, it opens a figure window with multiple tabs that allow you to explore lateral sweeps, longitudinal sweeps, combined slip, and friction plots at different inclination angles and slip angles. While the default plot gives us a good overview, there are times when we want to focus on specific relationships. To do this, we can use the plot function with name value arguments to customize what we want to visualize. We start with the plot command and specify the data variables name value argument followed by the variables we want to plot. In this case, ET, which is the elapsed time, and FC, which is the normal force. As you can see, the data appears noisy. To better understand it, we can add another name value argument, color by, and set its value to FC. Now you can see we have a better view. To clean up the signal, we can use the mean function to assign each tire data object a mean nominal value for the FC channel, which will help to reduce the noise for further processing. Similarly, you can plot longitudinal force versus longitudinal slip across multiple tire data objects. Suppose you now want to visualize the longitudinal force only for data points where the normal FC force lies between, for example, 4000 to 5000 Newton. You can achieve this by using the filter by and filter by values name value arguments in the plot function. As we run the section, we can see the plot between the force values specified in the filter by values. Similarly, you can plot longitudinal force versus the lateral force. Now that we have visualized the tire data, let's move on to the next major step, that is tire model fitting, which refers to the process of calibrating a mathematical model so that it accurately represents the measured tire data. Again, before jumping into the code, let's quickly understand why the fit type matters. This table shows different types of fits, along with their descriptions, recommended data, and dependencies. As you can see, there are various fit types such as FX pure, FY pure, FX combined, and more. Each fit type corresponds to specific data and real-world scenarios. For example, FX pure models straight line braking while FY combined captures lateral forces during braking in a turn. The fit type you choose depends on the tire behavior you want to model. So whether it's straight line braking, cornering, or combined slip conditions. So here is one important note. The order in which parameters are fit is important. If you fit a set of parameters that have a dependency to another parameter set, do not refit the upstream parameter set without refitting the parameter set with the dependency. Refer to the table in the documentation for dependencies between parameters. With that context, let's switch back to MATLAB and fit a tire model to our data. We have created a Magic Formula 6.2 tire model using the tire model.new, which creates a new tire model object. Further, we have set the dimensions and nominal test conditions and model limits. We use the fit function to fit the tire model. You will notice two fit commands in the code. First, we apply a general fit using dimensions to automatically set the dimensional properties of the tire to match the test data supplied to the model. Then, we specify the fit type as limits to automatically set the model parameters to match test data supplied to fit the model. Also, we keep the fzmin parameter value constant when these limits are applied by setting the fixed parameters argument to fzmin. As we run, you can inspect which variables were updated by viewing the diff table. Now that the model is initialized and aligned with the test data, we can proceed to fit specific tire behavior. In this case, we want to model the longitudinal force characteristics. So, we start by selecting only the longitudinal test from the tire data array. Then, we apply the fx pure fit using the fit method. By selecting plot fit to true, we can also visualize how well the model aligns with the actual test data. As we run this section, you can see the fit looks satisfactory. Also, the diff table again shows which parameters were updated during this fit. Similarly, we can perform other fit types, and you can also see the variables of the MF6.2 in the workspace. Finally, we can visualize the fitted tire model response using the plot command. Now that the fit is satisfactory, let's update the fitted tire model to the Vehicle Dynamics Blockset tire block. For this, we will use the set function. Here is the Simulink model with the combined slip wheel 2-DOF block. In the set command, we specify the fitted tire model object followed by the path of the tire block. Once we run it, you will see that the block has been updated with the fitted tire model. Alternatively, you can use the export method to write the tire model parameters from the tire model object tm to a tire file and manually update the Simulink tire block by selecting the generated TIR file from the current folder as shown here. You can also plot the steady state force and moment response by clicking on this plotting tab. Also, if you are working with Simscape multi-body models, you can use a set method to generate the scalar structure array expected as tire parameters in the magic formula tire force and torque block. By now, you should have a good understanding of the overall workflow using the extended tire features. In this second demo, let's look at some additional and useful functions. In demo 1, we imported the tire data using the TYDEX format. But what if tire data comes in different formats such as calspan DAT files, column-oriented text files, or CSV files, or even MAT files? To handle the calspan DAT files, column-oriented text files, and CSV files, you can use the tire data import function. There are documentation examples that demonstrate how to import calspan data files into a tire data object, and there is another example to demonstrate how to import CSV files and convert them into a tire data object. In demo 2, the tire data is saved into a MAT file, which are common in Formula Student competitions. And we will walk through how to use this tire data by following the similar workflow we saw in demo 1. The MAT file is already available in the current folder. We start by loading the file, and you will see that it contains data for various tire variables. Next, we create an empty tire data object. Since the source data is already in the SE coordinate system, we ensure that the object is aligned accordingly. Please note, if you're working with TYDEX or calspan files, you don't need to worry about coordinate transformations as they are handled internally and we just saw in the demo 1. We then populate the tire data object using the loaded tire data. Once populated, you will notice it is currently single tire data object. To work with multiple test conditions, we use the split function to divide it into an array of tire data objects. Since there are many data points, we apply the downsample function to reduce the sampling rate. Then, to clean up the FC data channel and reduce noise, we use the mean function, which is similar to what we saw in the demo one. Although the data is clean, you can use filter function to remove noise from tire measurement data. From here, we proceed with familiar steps, and those are set the dimensions, define nominal test conditions, specify model limits, and then use the fit function to fit the tire model. And finally, use the export function to write the results to a TIR file. As we run the code, we get a satisfactory fit, and the exported TIR file is saved in the current folder. Now, we will use the TIR file in the generate skidpad example model, which you can access using the link provided in the video description. We will first open the model using the command in the command window. Then we will navigate to the subsystem containing the tire block and then select the TIR file that we just exported. Once the TIR file is loaded, finally, we run the simulation to visualize the vehicle behavior as it drives through the skidpad test track. Now moving to the last part of our video, you can go a step further. You can log the vehicle data and use the Simulink 3D animation blocks to perform a comparative 3D visualization of vehicle motion, allowing you to directly observe the effects of different tire models on handling and behavior. For example, now in the generate skidpad test track example, we have two vehicles with different tire models, and we can see the effect of these on handling and behavior. So we have seen the programmatic API approach to using the extended tire features. Now, here's a quick glimpse of the Tire Manager app released in R2026A. As you can see, the app lets you fit the tire data. Once you start the fitting process, a fit schedule is proposed for your data. The app highlights any missing data. You can edit the fit schedule. Then watch the progress icons as it runs. Further, you can review the fit results and finally push the parameters directly to your Simulink model. If you would like to learn more, please check the video linked in the description. We hope this video provided a clear overview of how to use the extended tire features, from importing tire data to exporting the tire model for vehicle dynamic simulation. If you are interested in exploring further, please refer to the documentation pages linked in the video description. And also make sure that you are regularly checking the Vehicle Dynamics Blockset release notes to find some of the new and interesting features to be added in the future releases. Thank you.